You can start. Yes sir, yes sir.
काळे सर इंट्रोडक्शन देतात का कसं झालं त्यांचं?
Sir, I'll start, sir.
Okay, ma'am.
Good morning, all. I, Professor Ashwini Gutmare, on behalf of MCT's Rajiv Gandhi Institute of Technology and Department of Mechanical Engineering, welcome you all on this virtual dais for AICT AQI sponsored online short-term training program on recent trends in energy management and audit. Our today's speaker is Dr. Siddappa Bhusnoor, Professor in Mechanical Department at KJ Somaiya College of Engineering. Sir has completed his PhD from IIT Bombay. He is Certified Energy Auditor from National Productivity Council, BEE, Ministry of Power, Government of India. Sir has total 24 years of teaching experience and published more than 30 research articles in reputed peer-reviewed international journals. Sir has attended more than 20 STTPs and he is a life member of SAE, IST, and IE. Sir's research specialization is in thermal and fluid engineering, heat and mass transfer, and his areas of interest are IC engine, alternative fuels, heat exchanger designs, modeling of thermal systems, industrial applications of heat and mass transfer concepts. So, uh, also, HVAC, energy conservation management and energy audit, air pollution and control, generation and characterization of nanoparticles, design and development of renewable energy systems, design and development of industrial air pollution and environmental air pollution measuring control devices are his interests. Sir has received Best Paper Award in various international conferences. So, with this small introduction, I request our today's speaker, Dr. Siddappa Bhusnoor, to please start his session. Over to you, sir.
Thank you, Ashwini, for a nice introduction. Good morning to all. I am grateful to RGIT management, Principal Dr. Bokade sir, and Head of the Department, Professor Kali sir, and my dear colleagues of Mechanical Department for providing an opportunity to share a little knowledge what I know about the recent trends in energy management and audit. With reference to that, today I'm going to give a small presentation on performance analysis of a cogeneration systems. As already Ashwini has briefed, I am working with Somaiya Engineering College. Now we are private university under Somaiya Vidyavihar. Am I audible? Amol sir or anyone?
Yes, sir.
Is it voice is proper? Okay.
Yes, okay.
Can I go ahead?
Yes, sir.
Okay. So I'm going to present today's topic briefly in different contents, like starting from introduction to cogeneration systems. Means what is cogeneration, why cogeneration is required, and what's the use of cogeneration in improvement in efficiency of the different prime movers, and how the cogeneration systems are classified, and then what are the performance parameters of the coal systems we are need to measure or evaluate for comparison of their purpose or effectiveness, and what are the instrumentations required for measurement of the different parameters of the system, like prime movers or utilities or consumables, and then what observations are need to be taken while testing the cogeneration system for evaluating its performance parameters. Then it is followed by a small case studies, a few numericals, and then references what I used for this purpose or this presentation. We all know that the cogeneration is a concept, or it is sometimes also called as a combined heat and power system. In this case, we are going to utilize the energy from the same source for the different applications or the different ways after it has been used for the primary purpose. For example, if you take, I'll give an example of an IC engine. If you take an IC engine, initially the fuel has been burned in the engine for producing the power through via heat energy. Then later on, as the gas comes out from the engine exhaust, it's having a high temperature potential, then there is again so many chances for us to recover that heat energy and use it for different purposes. That's why there is so many definitions for cogeneration, but one of the common definition we can define as a production of more than one useful form of energy from the same source and use it effectively. And then what's the need? Why you go for cogeneration systems? Or why to go for recovery of, simply sometimes we can call it as also it is energy recovery concept, or generally it is known as waste heat recovery systems also. I think yesterday one of the speaker has explained about waste heat recovery analysis also. From the conventional power plants, we know that about 35% of the energy is coming out as a work output, which is one of the thermal efficiency we are defining. None of the heat engines, either it may be internal or it may be an external combustion engine, are having more than 38% efficiency. Basically, maximum Carnot heat engine efficiency we are not exceeding more than 54.6. Then what about remaining other form of energy which is coming out as in the form of waste? And therefore, there is a chance or a potential to recover this energy which is living as a waste to the atmosphere or to the any other media. For that purpose, it is always necessary to use the recovery devices to reduce the energy consumption or to take care of effective utilization of the fossil fuels available or any the renewable energy also. Then what are the major sources or losses in the conversion processes? The major sources or losses in the conversion process I just explained you. It is loss of energy to the surrounding from the system, either it is through via water media or maybe air media, and due to some of the inherent constraints or some of the what you call the nature of this system. None of the system is going to give out the whatever amount of energy input to that into a power output. As per the first law of thermodynamics, Q equal to U plus W. That means there is no work completely converted through via the heat. And some of the systems are having their inherent constraints, like if you want to transfer the heat from hot fluid to cold fluid through via either it will be the direct or indirect heat exchangers or indirect contact systems, then there is an internal resistance of the system plays the role for reduction in transfer of energy. And these are, and some of the thermodynamic cycles
Bhusnoor
also
sir.
have their inherent constraints. Like if I go to IC engine, then almost before expansion of the gas in the cylinder, I have to open the exhaust valve because I want to remove the exhaust at higher pressure from system to the surrounding. Otherwise, I have to give the work input to the system to expel the expanded gases. That's why these are the, like this, there are so many concepts where the cycle itself is having its inherent problems. And is there any ways for us to reduce these all losses? Then the loss of around 10 to 15% once the power comes out or the energy comes out from the thermal source and it has been converted into an electrical energy, then from point of production or from the place of production to the place of utilization, we have to transfer it or we have to transmit from point of source to the point of utilization. Then there is TDS losses again comes into picture, the transmission distribution losses. And this also, I think a few of the speakers explained in detail in the previous presentations. I think those who are attended regularly, I think this is one of the best platform that RGIT has started for all of us, at least for the thermal guys, which will get the more knowledge during the lockdown process. I'm really grateful, and I'm enjoying your all the courses.
Sir, Bhusnoor sir.
Ha.
Sorry to interrupt, sir. I think you have not shared your presentation, sir.
I see. एक but पहला presentation mode पे ही था, then I started.
No.
Sorry.
Yeah.
अभी देख लीजिए sir, please.
Yeah. Yes, sir. Now it is visible. Full.
Can I go by beginning now once again?
No.
Not necessary, na? Okay, anyhow, I am in the first slide. Is it okay?
Yes, sir. Now screen is visible, sir. Presentation.
Screen is visible?
Yes, sir. Yes, sir. Thank you, sir.
सर पहले थोड़ा रिमाइंड करना चाहिए था. वैसे जब पहला स्क्रीन मोड पे था, इसके लिए देन आई स्टार्टेड. Is it clear now?
Yes, sir. Yes, sir. It's clear.
Now, what are the principal cycles on which the cogeneration system works? The principal cycles on which the cogeneration system works, it may be either heat cycle or it may be in a power cycle. That means either it may be the production of heat energy and then utilization for the conversion into an power output, or first initially the primary power output, then to use the heat for the different processes. We all know that there are external combustion engines like a Rankine cycle and gas turbine power plants are going to work on Rankine or Brayton cycles. And these are the two basic systems, or the principal cycles are used in a cogeneration system. Now, how to differentiate between the cogeneration system, the direct systems. For example, let us have a look here. It is on the first graph, which shows you the generation of electricity. I am taking input as a fuel energy, converting into a power output through higher heat energy, and 40% being a optimistic, I am saying that 40% of the energy is coming out as a power output and remaining 60 will be wasted as a loss to the surrounding or from system to the outside. Now, in this case, this 60%, I may use it for different purposes if I use a concept called as cogeneration. And second, you go to the generation of heat, generally for different process industries where we are going to produce the heat in a combustion chamber and going to use it for either phase change processes like steam formation, or some other industries like in what you call casting industries, and anywhere where the thermal process is more important. In that case, for example, if I take the power generation as a boiler concept, we know that almost the boiler efficiency is from 80 to 85%. Then 85% of the heat energy produced in the combustion chamber will be coming out as a steam enthalpy, and remaining 50% will be lost to the surrounding. Now this 60 and 50%, which 15% which are lost to the surrounding, we have to use, if I adopt some concept called as recovery systems, and then that recovery system adopted whole system is called as a cogeneration system. Then in a cogeneration plant, the fuel which is supplied is utilized for different, either it is heating or for power production. Therefore, sometimes the cogeneration system is also called as combined heat and power systems. Combined heat and power systems. Now, generally in this case, almost 50% will be the heat, which is we are going to use it for different purposes, and remaining 40% will be comes out as a power. Either it is at high potential or it may be at low potential also, depending upon the concept or cycles, thermal cycles you are using for recovery of the heat into work output. This is what the basic difference between how individual systems like heating and power systems are different from cogeneration system. Generally, the cogeneration systems or these combined heat power systems are classified into so many categories depending upon, I already told you, the principle of operation. Maybe it is a Rankine cycle, maybe it is a Brayton cycle, or sometimes it may be a combined cycle, or sometimes it may be used for very low temperature devices like we are going to have low potential heat absorption systems also. We'll discuss when I go to the next slides. Now, there is no defined classification, but it depends upon how you are going to design a system for recovery of the heat. But even there are some basic principles on which the core systems are classified. One of them will be hello.
Yes, sir.
हाँ अमोल कुछ लोग एडमिट होते जा रहा है तो आई थिंक पॉपअप हो रहा है तो स्क्रीन में इट इज डिस्टर्बिंग इज देयर एनी वेज टू नॉट टू
Admit additional people.
हाँ नहीं नहीं is there any way to admit the people directly?
Yes, yes. Okay. Prathamesh, sir.
Now classification of cogeneration systems. Initially they are classified depending upon how I told you it is the way only how you are going to design a system for recovery of the energy, or the way in which you are going to produce whether utilization of the heat energy either initially for thermal process or it may be for power generation or vice versa. Depending upon that, the core systems are classified into two broad categories. One is called as topping cycle systems and second is called as bottom cycle systems. And again, these topping and bottom cycle systems are classified depending upon the principle of basic operation, whether it is gas power operated or it is a vapor power operated systems, or it may be rotary type or it may be reciprocating type. Then depending upon that, again, they are briefly classified into steam turbine, combined heat and power systems, reciprocating internal combustion engine systems, and gas turbine systems, and combined of either one of or all may be that is called as combined cycle heating and power systems. Now, why it is called as topping and when it is called as a bottoming system? Generally, in terms of a temperature levels, there are some necessity. Initially, I may going to use a thermal energy for different processes, like if you go to the casting and if you are melting system or furnace industries, and where we are going to use high thermal energy initially for applications. In that case, the exhaust or the waste heat which is coming out from the such type of industries will be having a higher potential, almost 500 to 600 degrees centigrade temperature. And this is one of the best source for utilization of this energy for converting into a power output. Now, if I have potential of 500 to 600 degrees centigrade, I can easily use this as an input for my power generation systems like Rankine cycle or for thermal power generation. Then later on, once that energy comes out and it is utilized, again, you can have a still chance to reduce its temperature up to 120 or 125 degree, 130 degree. And beyond that, we are not going to down it because of some other environmental problems. Once any gas will be used to the ambient, and it should have some defined temperature. Generally, we are not allowing to leave to the exhaust gases to the atmosphere below 120 or 130 degrees centigrade roughly. Till that, we have a chance to recover it. That's why if initially my application is thermal oriented or for thermal process, then I'm using that byproduct of that will be as a source of heat for the electricity generation. Then that type of systems are called as bottoming system. Generally, they are in process industries or in uh, melting industries or in casting systems where we are going to use the bottoming type of applications. In topping systems, the source of electricity, initially we are going to generate like all thermal power plants. Initially we are going to generate the heat or liberated heat from the fuel is utilized to convert into an A or enthalpy of the steam, and then it is utilized for power generation. Then the gases which are coming out from the exhaust of a combustion chamber or exit from the combustion chamber are used for different applications. I think in so many presentations, the speakers are explained in thermal power plants, generally we are having, initially we are having an economizer, then we are having an air preheater, and then again we have recovery devices for extracting the heat energy. Initially, the exhaust gas, high exhaust gas goes to the superheater, then goes to the economizer, then goes to the air preheater, and then again for small heating applications, we are going to use it, and then we are going to expel it to the atmosphere. And that means that's called as thermal process applications. Like if initially I'm using the high potential for power generation, then the low potential is utilized for different heating systems. Then that system is called as topping system in cogeneration. Now, here I have just explained whatever I have explained. It is written in text form. In topping system, high temperature fluid drives an engine to produce electricity, while low temperature heat is used for thermal process or space heating applications, or sometimes cooling. Cooling means you are going to run a refrigeration systems. That means we are having, you might have heard, nowadays we are having vapor absorption refrigeration system going to run at a low exhaust heat, exhausted from either it may be reciprocating engines or it may be any hot source. In that case, it can be act as a cooling application. In a bottoming systems, high temperature heat is first produced, I told you, for a process industries, and after that, that heat is utilized for power generation. And unavoidable, behind almost some 150 or 130 degrees centigrade temperature, we are not going to extract the heat energy available from the exhaust, and it will be lost to the surrounding. With this basic concepts, so now I'm just going to overview about what are the different types of steam turbine, combined heating and power systems, gas turbine power systems, and internal combustion power systems. Almost all we almost here, the maximum people are teaching community. I think we all are come across these systems in our regular teaching at different courses. And just I'll glance it, and we'll going to stress more on what about you can call it as performance parameter analysis, and then some case studies. And this system, initially the steam turbine systems, it's called as a back pressure steam turbine. The reason here, the steam which is exhausted from the turbine is utilized for the different process applications. In this system, the fuel initially burns in the boiler. The high pressure steam which is formed is utilized to do the work on the turbine. And then I told you almost 30 to 40% of the enthalpy energy converted into power output, and through via that power will be converted into mechanical energy, into an electrical energy through via AC DC generators as per the requirement. And then the steam at a high pressure or the exhausted pressure, generally depends upon from what point you are going to tap the steam or bleed the steam from the turbine. If you are tapping at high pressure, you are going to get a more enthalpy as well as the more pressure or the good quality of the steam, but you are going to justify it. And what's the purpose of tapping the steam at a high pressure and a high temperature or high enthalpy level? And then that high pressure or high enthalpy steam you are going to use it for different heating applications or some different processes. But anyhow, once the steam is expanded from high pressure to the lower pressure, then the specific value is going to increase. Then it's difficult or it's impossible for any system to take back that expanded steam back to the boiler drum. Therefore, as per the second law of thermodynamics, the system must work between the two different temperature levels. Therefore, we are supposed to use a condenser, and then condenser, through via condenser, the steam has been get condensed and specific volume get reduces to approximate initial volume of the liquid, and then that liquid is pumped back to the boiler. And like this type of system is called as the steam turbine cogeneration system, and this falls under the category called as topping system, because I told you in topping systems initially we are generating power and then we are using the heat energy. But in all the system, in thermal system analysis, generally we are adding electrical and heat energy together, and then we are saying it is a total energy taken out from the system. But generally, it's not the correct way to add two different energies and saying it as it's a total energy. But generally we know that the Q is equal to U plus W and W is not equal to Q. Then adding Q and W together and saying it as a total energy is not the proper way in terms of energy auditing or energy conservation process. Therefore, in generally for performance parameter analysis, we are going to use exergetic equations or exergy analysis. I'll explain when I go for performance parameter analysis of the cogeneration system. This is one of the Barack versus steam turbine arrangement. And again in steam turbine, we have second type is called as condensing steam turbine plant. Here you can see the line diagram shows you. Here again, it is again a topping system. Initially, the heat has been supplied in the combustion chamber and or the fuel has been burned, and the heat released from the combustion chamber is utilized to convert the water into a steam, and that high pressure and high enthalpy steam enters to the turbine. Now you see that here in the turbine, after or even during the expansion process, at different points we are going to tap the steam. The tapped steam at a high pressure and temperature goes to the heat energy or enthalpy energy for different heating applications, and then the exhausted steam will be from the turbine will be taken to the condenser, and again in the condenser it's going to release its latent heat of evaporation, then it gets condensed into a liquid. Now this liquid is having temperature, saturation temperature approximately at the condensate pressure or condenser pressure. If the condenser pressure is almost some what you call 0.8, 0.7 bar, and accordingly it may be around 56 or 60 degree temperature of condensate comes out, and which is again a good amount of low temperature potential heat energy available, and then this condensate has been pumped back to the boiler. That means this is called as condensing steam turbine power plant, where I am going to use it for different process applications as well as the what you call for the even I can allow the steam to expand to a very, very low pressure, because if I'm putting a condenser, the main purpose I am going to create a suction such that the steam has been expanded in the turbine to a as much as possible lower pressure depending upon the vacuum created in the condenser. Hello, am I audible?
Sir.
Prathamesh?
Yes, audible, sir.
Okay. So please remind me if anything.
Yeah. Yes.
Due to some net problem, internet problems.
Yes, sir.
Now, third type of the cogen system will be bottom cycle cone systems with a condensing steam turbine power plant. You see here it is called as bottomy because initially I am using the heat energy liberated from the fuel for thermal applications. And the high temperature, like I told you earlier in the previous slide where I am going to compare the temperature indices, the high temperature gases are used for thermal applications like in casting industries or in metallurgical industries. And then the exhaust coming out from that will be used in heat recovery, what you call the steam generator systems. There are some, this is called as heat recovery steam generator system. That means it is any one of the heat exchanger, because generally the boiler is also a heat exchanger. Nowadays, we are having application of what you call heat pipe heat exchangers. One of the what you call recent technology which we are using for extracting the heat at a high thermal conductivity media, which is the one of the heat pipe heat exchanger will act as a high thermal conductivity heating media, and that type of heat exchangers can be used for different applications like recovery of effectively the maximum amount of waste heat from the thermal processes. Now, once the initial purpose of using the fuel energy for thermal processes get satisfied, then that high potential gas will be sent to the boiler. Depending upon the temperature of the gas, the liquid used in the boiler may depends. If you are having a temperature maybe around some 607 degrees centigrade, then you can use water. But depend upon at what pressure you want to evaporate it. Then your pressure and the input temperature, the pressure requirement in the boiler and the input temperature of the exhaust gas plays the role, the how much pressure of the steam you can generate in the boiler. Depending upon your requirement of the steam pressure and quality of the steam, you can change the operating parameters as well as the device also. Or if you want more pressure, you have a less potential heat energy, then you can use the low latency type of evaporation fluids like some other than water. We are using the compounds like toluene and other things which are going to evaporate at a lower temperature. Then they can become the one of the media for working as a vapor power cycle, working media for vapor power cycles. Then that vapor will expand in the generator, in the turbine. Then power will be produced. Then later on that exhaust will be used for different applications. Then this is called as bottoming cycle cogeneration system. Because initially my main objective is to use the heat for thermal applications. Then the waste heat will be used for power generation. Then sometimes this may be also called as combined heating and power system. But in that case, we are going to use both. Generally, in combined heating and power systems, we are going to use both the cycles, like your Rankine cycle and Brayton cycle. I just told you, depending upon the heat potential available, we can use the organic fluids also as a working media. If the heat potential is very less, then you can use the organic fluids for changing their phase and converting into vapor at high pressure, then taking the work from that. Generally, these organic fluids are used in where high quantity of the low potential heat source is available. Like best example is geothermal power systems, where we are having the very less temperature difference, but the flow quantity or the quantity of the fluid is very high. In that case, we can use the organic fluids for generating the power. When a heat is available at a relatively low temperature, almost some 80 to 300 degrees centigrade, organic fluids with a low evaporation temperature can be utilized, such as toluene. In organic cycles, effective in geothermal applications where only low temperature heat is available. In certain cases, the working fluid can be a mixture of two different types of fluids, because even if you want to extract the low maximum possible amount of energy from the exhaust gas, for example, in these thermal applications, the figure which I shown to you, if the exhaust temperature is around 600 or 8 degrees centigrade, initially I can use the water as a fluid for converting for extracting the heat from the gases. And then if the gas comes out at around 300 degrees centigrade or 350 or 400 from the first heat exchanger, then I can use the low evaporation, enthalpy of evaporation fluids like organic fluids. But again, I can extract the heat from that 300 or 350 degrees centigrade exhaust gas, then use it. It has once again the second set of generator, either at low pressure or at a low power. Like that, I can have a series of power generation systems depending upon the potential amount of heat available for me, which I'm extracting from the exhaust gas, but source for all these will be the single source as a thermal process. And then organic fluids have two major disadvantages. The major disadvantages of the organic fluids are they are more expensive than the water, because water is easily available, or not. It's not easily available nowadays. It's becoming costlier. Even if you use for free available water, then you have to treat a lot because of lot of water pollution problems you are facing. And the fluids such as toluenes, and they are hazardous to materials to the environment. You know that nowadays we have been banned the CFCs and other things from the refrigeration system or HVAC systems because of their impact on the environment. Generation and producing the energy is not the problem, but at what quality and at what cost we are going to produce or generate it. That's the most important. Nowadays, we are putting more emphasis on pollution control, the one of the emerging area, and which is one of the emerging field in energy intensive industries also. And therefore, the more concern will be given on pollution control in terms of effect on health, human health, as well as on the effect on the environment. And also environment includes everything, air, water, and structures also, that it's our duty to look into that. Being in an engineering community, we have to take care of all while whatever the process or activity we are doing in our technical systems. Now, the second classification of the ozone system will be the use of gas turbine cycle. I told you we all studied or we are teaching in the courses, different courses, how the gas turbine power cycles are classified. They may be open cycle, they may be closed cycle, or sometimes generally in all gas turbine power plants are generally they are maximum they are open cycle. Closed cycle may be at a lower capacity. And this gas turbine is again a topping system, because the here the combustion, initially we are producing the heat energy by, or we are extracting the heat from the fuel by combustion in the combustion chamber. Then the burned gases at high pressure, they are made to expand in the turbine, gas turbine, and then exhaust from the gas will be utilized for different thermal applications. Depending upon the potential of the exhaust gas, at what temperature it is available, then you can use it for some, for example, if its temperature is very high, then you can use it for steam generation. Then again, you can run one more steam turbine from there. Or if it is a low pressure, then you can use it for different heating applications. And then you can, if it is again still low, then you can use it for heating the air, because generally the air which we are sending it to the combustion chamber, some devices you can use the hot air also of different applications. But using air in the gas turbine power plants at a hot air at the initial condition will affect a lot on the compressor power. Therefore, generally we are going to take the air from the atmosphere, which is a minimum possible normal temperature of the air. As much as the temperature of the air will be the lower, then the work input to the compressor will be reduces, and the power obtained or heat release in the combustion chamber increases, because you are getting more dense air, and the more mass of the air will be get inducted. On the contrary, if air temperature increases and inlet to the compressor, then you have to do the more work into the compressor, then automatically then your thermal efficiency of the overall system will be get reduces. Taking this into account, then we have to ensure what type of energy is required and how to extract it. A natural gas turbine, here that drives the generator, the exhaust goes to the different recovery systems. And this is one of the cogeneration system which is applied for gas turbine power plants. Now here the gas turbine is in an open type, because the exhaust will be expelled to the atmosphere after recovering the heat at different levels. Then in closed system, I told you the media is now, it's not media which is expelled to the atmosphere. The working media in the system will going to change its phase from sometimes vapor to liquid and liquid to vapor and so on. Sometimes even in generally in an aircraft air refrigerations and other things, we are using closed cycle gas turbine, but in a smaller capacity. But it's to avoid the some other what you call some operating problems, then we are going to sacrifice there the power. And in that case also the air is also sometimes used in the closed system, but it's not regular practice. The here one of the working media will be different from that of the air, and low enthalpy operation media will be utilized, and then it is compressed in the condenser, and then it enters to the heat exchanger, where the heat has been Now we know that whenever the closed system, whether it is internal combustion or it is external combustion engines, but generally in gas turbine also we are having in a closed system. Here it is a closed system, is an external combustion. It's in a external combustion, but the system is a closed one. Though in that case, there is no direct contact of the fuel and the media. But generally, as in IC engines, we are directly injecting the fuel inside the air, and the fuel is burning, and then burned gas will be made to expand on the piston head. But in open cycle gas turbine also, the air and fuel both are mixed together, and high pressure and high temperature gas is made to expand on the turbine. But in closed systems, the heat will be supplied externally to the media. Then the media's working media's enthalpy and pressure will be increases. Then it expands in the turbine. Then later on, after that, it will enters to the heat exchanger. Now here the heat exchanger maybe depends upon what type of heat exchanger you are using. I told you a minute back. The boiler is also one of the type of heat exchanger. Depending upon your type of application, it may be at what temperature level you are going to operate it. Now, if you are using a very low rate of evaporation fluids in the boiler, then the exhaust heat from the turbine or the exhaust media from the turbine may be able to evaporate that media in the heat exchanger, and then that evaporated fluid you can take it for the power generation once again or for any other applications also. So then this is the way how we can going to extract the heat from closed cycle gas turbine and use it for different work as well as heating applications. Third type, you all know that we are going to run a DG sets, diesel generator sets for as a power generating units at some places where we are not having a grid, or that it's a difficult for use a grid connections, or difficult to use the power transmission lines like in hill stations or some other places. In that case, generally the diesel generator sets are using as a supplementary devices for producing the power or electricity. Now we all know, probably being in teaching line, at least we have an idea, 2-cylinder, 3-cylinder, 4-cylinder diesel engines were operating in the systems. Maybe if somebody is getting a chance to visit any thermal power plants, they are using a DG sets as a standby units for running the auxiliaries whenever the plant is under shutdown conditions. Now, these diesel or any gas powered engines, whatever the power they are generating, for example, if you take in an IC engine, what we are generally using in our laboratory scale level, the heat is applied inside the combustion chamber, and that burned gas will do the work on the piston head, and then fraction of the heat which is liberated during the combustion process will be carried by the jacket water, because as a combustion chamber is go on absorbing the heat during the combustion process, then it is necessary to keep or carry away the heat absorbed by the combustion chamber wall and keep the wall at some constant temperature. Otherwise, there is a problem called as piston jamming and burning of the piston liner and the piston rings will going to take place. Then sometimes the piston may get jammed due to overheating. Therefore, the jacket cooling we are going to use, and after that, that means some of the heat will be taken away by the jacket, and some of the heat will be lost in the form of a blow-by, and some of the heat will be expelled to the atmosphere through the gases. And again, probably we are using a small heat balance heat concept for recovering the exhaust heat from the engine exhaust. We are using a term called as calorimeters, and there it is nothing but it's a heat exchanger, or it may be saline tube heat exchanger, or it may be coiling tube type of heat exchanger, anything depending upon your requirement you might have used it. And then we are going to extract the heat from calorimeter, or we can again extract the exhaust heat from the exhaust gas through the heat exchanger, and that can be used for different applications. And the engine power output, which is we are getting as a brake power, we may use it for different purposes, like some tractive effort, like in automotive vehicles we are using it for tractive power, And in DG sets, we are using to generate the power. And as the engine is directly coupled to the generator, and the generator speed has been maintained around 15 RPM to get a power output at 50 Hz and 220 to 230 volts, then we'll get the electricity. And this power will be utilized for different applications. And the heat recovered from the exhaust gas can be used for heating and hot water supply. Or if you have a jacket cooling water and whatever the hot jacket water comes out, you can use it for heating and other purposes. And the gas which is coming out from the engine, you can use it for heat recovery from, again, HSRG devices like what you call, I told you a minute back, it is heat recovery steam generator systems. And then you form a steam or produce the steam and use that steam. Maybe you'll get a low pressure steam at high quality, or the low quality steam at high pressure, depending upon your requirement. And then the gases will be exhausted to the atmosphere through via chimney or stack, depending upon where the plant has been located. Now, this is what utilization of an internal combustion engine exhaust energy for different applications, for power generation, for heating and water supply, other conditions, for process steam heat generation. And then it is called as the internal combustion engine cogeneration system. And it's called as internal combustion engine cogeneration system. Now, with reference to this, I'll go to one of the case study of an IC engine has been shown to here for your just for kind reference. Let us see, you are having an engine here, and that means generally what actually the thermal power plant or in gas turbine power plants we are supposed to do. We are going to generate in gas turbine plants. We are going to generate the high pressure gas at higher enthalpy. But as the gas will expand in the turbines at different stages, the enthalpy of the gas will be going to decreases and the pressure decreases. But again, to get a work done, the increasing pressure is not possible, because as the gas is expanding, the specific value will be increasing. Again, for increasing pressure, you have to compress it, and we are not going to. It's impossible to work in the reverse to the thermodynamic process. Then only thing we can do is we can increase the enthalpy of a system. Therefore, in gas turbine power plants as well as in steam turbine power plants, we are using a concept called as reheating, staging of the steam turbine or staging of the gas turbines. That means the staging means what? We are just adding an external heat to the system. At that pressure, at what pressure the gas is available to us. If you can use that concept here also in any IC engine. For example, from the engine exhaust, you see there is a fuel supply to the primary fuel is supplied to the engine, and from the engine the power output will be coming out, and that power or the shaft power of the engine is utilized to run the generator, and the generator produces the power, and that power will be used for different applications. And then as the gas comes out from the from the engine exhaust, you can use it for what you call HRSG system. That means the heat recovery steam generators. And now if you use it in HRSG systems, then afterwards, whatever the exhaust coming out from the HRSG system, it is sent to the atmosphere. But as the part of the gases, then which is coming out from the SRSG system, if you use it in an auxiliary boiler is nothing but a boiler in which it's in a standby system in which we are going to add some fuel and burn this fuel gases which are coming out from it and add the enthalpy energy, and then auxiliary boiler is going to do more heat, and again the output from that we are going to take for different applications, and then you will get a hot source of energy. Then you can use it in the form of a heat system, and that means this is the way how at different stages, if you don't want to leave the exhaust gas to the atmosphere at a higher temperatures, then at every stage you can use it for increasing its enthalpy energy until its pressure goes to as much as possible low. Or if the pressure is not the criteria, you are not using it in a expansion devices. Once you are using it only in a heating devices or in heating applications, then you can use that gas till it attains to the atmospheric temperature maximum. Almost if it comes down to 40 or 50 degrees centigrade, but you are not allowed to, if it's a harmful gas or if it is a CH compound containing gases, you are not allowed to leave it to the atmosphere, because the products of CH compounds may be H2O and CO2 is not the harmful, but NOx, other polyaromatic hydrocarbons and other things which are, and also some particulate matters which are harmful to the environment and health, then you have been requested to treat it, or you have been allowed to leave it to the atmosphere at a higher temperature, because to avoid their condensation in the atmosphere. For that, it's always advisable to leave the gases at a higher temperature. And then fourth type will be the combined cycle cogeneration system. In a combined cycle cogeneration system, I told you we are going to use two thermodynamic cycles together. One is for using for what we call the Brayton cycle, and one is for the Rankine cycle. And then if these two together combined, then it is called as प्रथमेश थोड़ा लोगों को एडमिट कीजिए ना प्लीज. Amol sir.
Hello.
Ashwini madam.
Hello, sir. I'm
Yes,
audible.
sir. Yes, sir.
Anyone of there online, please admit the peoples. And now, in this system, two thermal cycles are used, which are connected together, and they may be operating with a different fluids also, and at different working media and different potentials, temperature potential. It may be a combined topping, or it may be sometimes it may be in a bottoming. The high temperature cycle rejects the heat. For example, if you take the gas turbine, which is recovered and used by low temperature cycles, like you can take it as in steam turbines, to produce electrical energy, and then later on that exhaust will, you see here, initially I am having here the gas turbine, and the fuel is supplied in the combustion chamber. You all know that the air compressed air enters at high pressure, and the injected fuel will burns in the combustion chamber. Exhaust gas will be taken to the turbine, and the exhaust from the turbine is used for HRSG system. Now here it will be act as a boiler, and from this the steam which is formed, it will goes to the turbine, and then from that the power output will be generated, and the exhaust steam will be taken back to some process industries. And then the exhaust gases from the turbine, they are going to send it to the different heating applications, as well as through high HRSG, and the condensate which is coming out from the condenser again pumped back to the boiler, or in SRSG system it is boiler. And like this, we are going to use energy available at different stages in as per their potential for different applications. By doing so, we are in a position to increase the overall efficiency of the plant. Even the thermal goes up to 85 to 90% also by using the cogeneration system. That's why in the beginning slides I shown you, in cogeneration systems you are only going to expel 10% of the energy to the atmosphere or to the surrounding, which is not possible to recover it, which is nothing but we start discuss that, which is an unavailable energy as per thermodynamics. It is T into delta S. Now this is one of the combined cycle, one of the study. This I got it from International Energy Agency booklet 1988. They published this. This book is this what you call the article or the book is very nice. They explained thoroughly how to test the cogeneration systems and how to evaluate the performance of the cogeneration system. You can see here, there they are using the initially, if you want to understand how this they combined it and they have brought it to, you see that generally they expelled the exhaust to the surrounding by 75 degrees centigrade. The initially their systems will be, they are using a gas turbine and the almost equivalent of 281 megawatt of energy they are inputting in the combustion chamber, and the exhaust from the gas turbine will be used to run the different auxiliary units. The initially the gas turbine which is producing the power will be going to run the generator, and this generator again, because they are having a multiple systems, they have cascaded it or they are combined it. And like in our, for example, in our internal combustion engines, we are using in a multi-cylinder engine, then all the what you call the to and fro motion of the cylinder or the rotary motion of the crankshaft is used to run a single shaft. That means they are going to combine all the power output at a single point. Like this, all the power output from the entire system, whatever they are using, they are going to use it for a single generator. And you see the exhaust from the turbine will be sent to the different systems. Like initially, they are using it to a high pressure steam formation. That means then later on, they are having a NOx amendment unit. That means where they are going to what you call reduce the temperature, then automatically the NOx emissions will be reduces. Then they are using sending it to the second boiler, then where again they are going to convert the heat into a once again using the steam. The low pressure steam comes out, and then that low pressure steam they are using at different stages of the turbine. Like this, they are having the combined steam turbine or multi-staging steam turbine. The steam, once it is expanded at different points, will be extracted back and reheated at different status at different pressure as per the potential of the exhaust gas from the gas turbine is available. And then later on, the condensate which is coming out or the exhaust which is coming out of the steam turbine, also they have used it for condensing at different condensers, and the total condensate is there again pumping back depending upon the heat potential available in the exhaust gas at different points, they are reheating it. Like this, in general, overall, they are reducing the temperature of the gas turbine exhaust to almost 75 degree and bringing it and sending it to the atmosphere. Now, here they are using a fuel as a natural gas, and calorific value, gross calorie electric power generating will be 129 megawatt electrical. Electrical power for auxiliary is running, they are using 1 megawatt electrical. Net electrical power they are going to generate 128. Thermal power they are going to generate 120 mega thermal from the steam turbine power plant. And they are having electrical efficiency 45%. Total efficiency due to cogeneration they have been increased into 88.2. And power to heat ratio, I will explain you when I go to the performance parameter analysis after this slide. The power to heat ratio, that means what is the ratio of electrical power to the thermal power in a system, then it is 1.07. Always the power to heat ratio should be in the range of almost some 0.6 to 1.6 depending upon whether the system is bottoming type or whether the system is your topping type of system. Prathamesh sir, any queries or doubts, or can I proceed?
Just proceed, sir.
Can I
At the end
proceed?
of yeah. At the end of session, ask some queries, doubt.
Okay. And next one is how one more combined power systems, if it is run by an IC engines. I told you in the previous slides also, what are the different ways the internal combustion engine exhaust gas can be used for different applications. And this is the line diagram or the block diagram for explaining the use of IC engine source as a point source or a resource for power as well as the heat generation applications. You see, power output will be utilized to run the generator, and then the coolant coming out from the engine is sent, or if you take energy levels into account, the exhaust gas coming out from the engine is sent to the heat exchanger, and the coolant is also having a temperature depending upon now how you are going to increase the temperature of the coolant. For example, it is a two-way multi type of heat exchangers now supposed to use. Here they have shown only one heat exchanger. It's not one heat exchanger, it is a two heat exchangers. One heat exchanger for extracting the heat from the coolant, that coolant is coming from the engine jacket, and one heat exchanger that is extracting the heat from the exhaust gas coming out from the engine exhaust. And then both the heat energies, probably the media of carrying the heat may be the same. Then later on, that heat will be sent to the low pressure system, and initially the power which is liberated in the combustion chamber rather than IC engine will be sent to the boiler, and then doing the work of the turbine. Then the exhaust from the turbine and the exhaust from the engine together they are combining, and that low capacity heat they are sending it to the application for as a heat source for different purposes. Now here in this case we are generating electrical energy as well as we are generating the thermal energy for different applications. Hence it is one of the best example for combined heating and power generation system, and which is based on your both steam turbine power plant, and again sometimes you can have, depending upon your requirement, even you can run the turbines from engine exhaust also, what we are discussed in earlier HRSG systems. This is the brief study what we did till now. What are the advantages and disadvantages of the various cogeneration systems? Initially, if it is a back pressure turbine, the advantage will be high fuel efficiency rating. Disadvantage will be it is a little flexible in design and operation. In steam turbine and fuel firing in boiler systems, if you see, it is a simple plant, but well suited to low quality fuels. And in this case, you need the more capital investment and low fuel efficiency, because if it's a low fuel firing, then low fuel efficiency rating. Cooling water demand, more impact on environment, because if you use the fuel of low quality, then automatically the emissions from that will be the more than you are going to treat that gases and leave it to the atmosphere, then it's going to impact more on the environment. And high civil construction and cost due to complicated foundations required, because you know that steam turbines and gas turbines, they are rotary systems, and balancing the rotary masses at a high speeds, and whatever the what you call the vibrations are the extra loads acting on the system's body can be transmitted to the, and they may be damped it, and damping will be requires the complicated civil construction. Gas turbine with a waste heat recovery devices. Actually, waste heat recovery system is one of the, once again, the broad area where we can have a lot of chances for different ways we can going to recover the energy. Here, good fuel efficiency, simple plant, low civil and less delivery period, less impact on environment, and high flexibility in operation. But disadvantage will be moderate part load efficiency, limited suitability for low quality fuels. And if you go for the combined gas and steam turbine power plant system, optimum fuel efficiency rating, relatively lower capital cost, and less gestation period, quick startup and stoppage, less impact on environment, and high flexibility in operation. And average to moderate part load efficiency and limited suitability for a low quality fuels, which is one of the disadvantages of a combined system. And if you go for diesel engine operated combined systems, low civil cost due to block foundations and least number of auxiliaries, and high power efficiency and better suitability as a standby power unit wherever you are facing a problem called as grid connections and other and thermal power system installation. And if the problem of water, and then again you can use sometimes DG sets for power generation. And then low overall efficiency, you know that generally the IC engines are almost none of the IC engine is exceeding 32 or 33% thermal efficiency. Limited suitability for low quality fuels, and because you can't use very lower qualities, like the worst case we can go for diesel oils. Nowadays we are going for a raw oil also. Directly we are going to use in diesel engine, but the life of the engine will be reduced, and also emissions will be also great higher in rate, like in terms of particulate matter and gases emissions. And then again treatment of that gas to before leaving it to the atmosphere cost a lot, and therefore availability, limited suitability for low quality fuels. With this brief understanding about what are the different types of cogeneration systems and how they are going to work and what is their basic principle and how to extract the energy in different ways, then it is necessary for us to analyze any thermal system or cogeneration system. We should understand some performance parameters, or we should know what are the parameters and how we are going to compare their contribution for the purpose, or how we are going to compare their for which objective they are meant. And in that case, you have to define some performance parameters. For example, for any IC engines, we are using thermal efficiency, we are using brake mean effective pressure, we are using BSFC as a performance parameters. Then in cogen systems also, we are going to use some performance parameters, but these all performance parameters are commonly, they may be their own efficiencies of the instrument. Like if you go to steam power plant, we have a efficiency of the boiler. We are going to analyze the efficiency of the condenser. We are going to analyze the efficiency of the gas turbine, sorry, the steam turbine. Then again, we are going to discuss about what is effect of what you call how the steam turbine will impacted if the pressure of the condenser is going to change, or condensate back pressure effect on that. These are all parameters we are going to correlate with the overall efficiency of the plant. And then we are going to discuss about what is the combustion efficiency in the furnace, and how much amount of fuel is supplied, and how much amount of the fuel is burned, and how it is extracted in different ways. And then how the engine, the exhaust gas coming out from the furnace is utilized in economizer, utilized in AP heater, and it may be utilized in superheaters or in the boiler system itself. And we are having their own inherent, their own efficiencies and other parameter to compare. Along with that, few of the parameters will be get added here, and that I'm going to cover it. And initially, before going to the performance parameters, let me explain what's the purpose of cogeneration plant performance test. Why you have to go for testing of the cogeneration plant. The purpose of cogeneration plant testing is to determine the power output and the plant heat rate, is to determine the power output and the plant heat rate. That means what is the output of the turbine, what is the output of the entire plant, and what is the heat rate at how much amount, and the efficiency of individual components. I told you just it's steam turbine or it's a gas turbine, specifically where their performance deterioration is suspected, for which reason they are not performing properly, and to compare the plant performance with the baseline values arrived at for the plant operating conditions rather than the design values. Generally, every system is having two values. One is a design value for optimal its output. It has been designed at high pressure and high temperature or high power output, and there are some the baseline values for which it is designed. For example, we can say the engine will use the more power at 5000 RPM. The engine is used the more power at some 75% of the load. These are called as the baseline values. Now it is always mandatory for us to test the equipment at a baseline values, whether it is giving that amount, rated amount or not, or that specified amount or not. Designed values are different. If I say the 40 HP engine, the 40 HP you are going to get when you run it at full load and full speed, or at its extreme conditions for what it is designed. Now that is called as design value. And then if you are going to operate at a rated the baseline values, then always it is better to check the baseline value and whether it is fulfilling the baseline conditions or not. If not, then the test of the purpose of performance test is necessary. And to show the maintenance accomplished after a measure overall, that means testing is required, because otherwise if you do not test the systems, you will not get when the maintenance is required for that, and what's the problem with that, what type of maintenance we are going to carry out for the improving the efficiency or the performance of the system. Understanding, because of this, there is a need for go for performance test of the systems. But in some of the cases, the purpose of evaluation could even be for a total plant revamp. Sometimes you may get a test result such that the entire power plant has been revamped. Then in that case, it is very this stage is the very crucial stage then to take the decision whether is it possible to improve the systems or we are going to revamp the systems. To reveal thermodynamics performance of these all systems, because once you are testing, that means you are analyzing the thermodynamic performance of the systems, and to facilitate the comparison of alternative solutions, that means before going to the suggesting, look, this is the problem in this case and this needs to be done, and before that we have to define some performance parameter on which parameter will be required to say this is not working properly. For example, if I take an IC engine, the mileage given for me for an engine BSFC, maybe I can say it is 0.45 kg per kilowatt hour or 0.24 kg per kilowatt hour. This is the defined range of BSFC for a diesel engine. But if my BSFC comes around 1 kg per kilowatt hour, then I can say I will convince the owner, look, the engine is consuming more amount of the fuel. It is as it is rated for 0.24 to 0.45. Now it is taking 1 kg per kilowatt hour power generation. Then better you can either change the engine or you have to overall, or you have to go for major maintenance of the engine. Like this, to say something is not working, you should have some parameters in your hand. And what are those parameters? And they are called as performance parameters. And what are those performance parameters? We are going to generally test, measure, or calculate, or evaluate. And one of them will be the efficiency of the prime mover. We all know prime movers may be gas turbine, steam turbine, or diesel engine. In all three systems we have discussed. Then it is mandatory you have to check how the prime mover is working. And you might have already known that they are having their internal efficiencies called as an isentropic efficiency of a prime mover. For example, if you can go to gas turbine, you are going to define what is isentropic efficiency of the compressor, what is isentropic efficiency of the turbine, what is the combustion efficiency of the combustion chamber, and what is the ideal efficiency of the turbine, steam turbine, what is the actual efficiency of the steam turbine. These all are called as prime mover efficiencies, and they may be their own internal efficiency or they may be their overall efficiency. Then one of the parameter we are going to define the prime mover efficiency data. We know that it is the work output divided by the total amount of heat energy supplied to the system. And here the work output is nothing but the WS is shaft power of the prime mover, and the amount of fuel supplied is a mass of the fuel into its calorific value. Flux fuel power, nothing but it is the calorific value consumed by the system. Then generally you can say the thermal efficiency can be expressed as the work output divided by the heat supplied, and then it's the mass of the fuel MF, and HV is the calorific value. Generally, we are going to use lower calorific value at all the cases because higher calorific value is only a laboratory determined value, but we can't get the higher calorific value from any combustion device. If you burn any type of the fuel, always we are getting lower calorific value. In this second parameter we are going to discuss about is what is the overall plant performance parameters. In overall plant performance parameters, one of the term we are going to discuss is overall plant heat rate. That means how much amount of heat the plant is giving out as an output by taking input as some amount of energy. That means the mass flow rate of the steam, if I apply it to the steam power plant, into the change in enthalpy of the steam divided by the power output which is given to the system. So then this will give you the overall plant heat rate. That means how much amount of heat you are just going to liberate in per kilowatt power generation in the system. And out of that, you will going to get a corresponding power output from the system. Then this term will be used for overall plant heat rate analysis. And second, overall plant fuel rate analysis. We know that the fuel consumption is nothing but in kg per hour, or we are going to define the term called as, in IC engines, we are going to define the term called as BSFC, brake specific fuel consumption, which is nothing but kg per kilowatt hour. That means amount of fuel consumed in kg per kilowatt power generated in an hour. Then in that case, in the plant also, we are going to define the term called as, again, similar to the BSFC, or we can call it as sometimes as a SFC, specific fuel consumption, which is nothing but the overall plant fuel rate. That is fuel consumed in kg per hour divided by the power developed. And here the fuel consumption we are taking, it is for total fuel consumption for turbine as well as for the steam power plant. If you are using some auxiliary boilers and you are using the fuel at different points, I have shown you already in the combined gas turbine power cycle. That is one of the literatures. I took it from outside journal. There they are using auxiliary boilers, and everywhere they are going to use the fuels for increasing the enthalpy at low pressure. Then in that case, all the fuel wherever you have spent in the entire system will be taken into account, and that comes under the heading called as fuel consumption. And then automatically your overall plant fuel rate will be suits up, or you will get an actual value of the SFC, specific fuel consumption of the system or the plant. And second prime mover, maybe your steam turbine. I told you just a minute back, we are going to determine the actual efficiency or isentropic efficiency of the turbine. Then turbine or cylinder efficiency can be actual enthalpy drop divided by the isentropic enthalpy drop. You know that always in actual enthalpy drop, due to some friction, either it may be in a steam turbine, maybe friction in the nozzle, maybe the losses in the moving to fixed blade, maybe the losses between the fixed blade to moving blade passage. And due to these all reasons, there's impossible to get a isentropic enthalpy drop. There always the enthalpy drop will be actual. This is a reduced. And that loss of enthalpy will going to give us a less work output. And then that is called as an actual enthalpy. And the maximum possible enthalpy drop will give you the efficiency of the turbine. Now, similarly, I told you what is the gas turbine. This gas turbine unit consists of a compressor, turbine, and a combustion chamber. Now here also we are going to discuss about isentropic efficiency of the compressor, isentropic efficiency of the turbine, and then isothermal, or what you call the combustion efficiency of the combustion chamber. And these all three efficiency will be need to be measured, and accordingly what you call the suggestion or maintenance can be carried out, whether the efficiency will be now decreasing or increasing depending upon what's the problem in decreasing efficiency, or what are the losses, whether there is a compressor leakage will be there is no pressure build up properly in the compressor, or maybe there is problems in the gas turbine systems, like the problems in the combustion chamber, that you'll have a different monitoring or measuring devices at different locations, and accordingly you have to record the observation and get back to the system for its improvement. If you are not going to get a baseline values of that system. Then heat recovery steam generator performance parameter. That means you are using an auxiliary boilers. In that case, you can use what is the efficiency of the generator. You know, this efficiency of the generator is nothing but it is the efficiency of the boiler. Hello. Sorry. आप बाद में please call कीजिए. I'm in the class. Sorry, there is a heat recovery steam generator efficiency. It is nothing but the boiler efficiency. You know how to define the boiler efficiency is nothing but it is the total amount of heat carried by the steam divided by the amount of heat supplied in the boiler. That is, we are going to define it. It is the product of ratio of mass of the steam to the mass of the fuel burned into the change in enthalpy of the water divided by the mass of the fuel into calorific value. And that will give you the heat recovery steam generator efficiency. Then accordingly, wherever you are supplying heat, and that you have to count it. Then here in the mass flow rate of the flue gas into Cp into delta T, he has used it. This may be, as it is a HRSG system, the Q equal to mCp delta T. Now here the M is nothing but the mass of the gases. We are using specific heat of the gas into change in temperature of the gas in the system. As it enters to the HRSG system, the gas will be cooled down by transferring the heat to the surrounding. Like in IC engines, we are using a calorimeter. As the exhaust gas enters to the calorimeter, the heat will be absorbed by the calorimeter fluid and the gas will be cooled down. Then that will give you the amount of heat lost by the gas in the calorimeter. Similarly, as you are sending the waste gas to the HRSG system, then the heat lost by the gas in the HRSG system will be mCp into delta T plus the auxiliary fuel consumption into calorific value of the fuel. Because this amount of heat lost by the gas in the auxiliary boiler is not sufficient to boil the media and convert into vapor. Then in that case, you are going to induct or you are going to inject the extra fuel in the auxiliary boiler systems and you have to burn it and you create a heat and that heat will be supplied to the boiler media or the boiling media and converting that media into vapor. In that case, you have to add the amount of heat supplied by the auxiliary or extra fuel for coping up the steam formation process in the system. Therefore, in the denominator, he has given heat lost by the gas in the HRSG system plus heat supplied by the fuel in the HRSG system is a total amount of heat supplied in the HRSG boiler, and in the numerator he has given the total amount of heat energy carried by the steam, mass of the steam into change in enthalpy of the water. That means depend upon now whether the steam coming out from the HRSG system is a wet steam, dry steam, or it may be a superheated steam. Depending upon that, your delta H may be H superheat minus HF or H saturation minus HF, or it may be H wet minus HF. Like this, you are supposed to calculate what is the total heat carried by the steam generator. Total is carried by the steam from the boiler. Then these all first part of the efficiencies are related to our thermal system. Then the term comes into the electrical system, the conversion system or electrical efficiency. How much amount of equivalent electrical energy I am getting by supplying certain amount of heat input in the system. Then that term we are going to define by a word called as electrical efficiency, neta E, where WE is a net electric power output from the system. If, for example, from a thermal power plant, I am getting out of putting 100 units of heat energy, if I get 35 units of power output from the generator, then the electrical equivalent is 35 units. Then what is the total amount of energy I'm going to supply is 100, that mass of the fuel into calorific value. Then sometimes it's also, you can call it as generator efficiency, or sometimes you can call it as overall efficiency of the plant also. And then how to define thermal efficiency? We know that it is the amount of, but because why you are going to use a different terms here, the thermal part is related to how, whether I'm going for bottoming system or I'm going for the topping systems. Depending upon that, my electrical efficiency as well as my thermal efficiency is going to change, because my source of heat input will be the same. And that source of, from the same source, I'm using either for part of that for the power generation and part of that for the heating applications. Now, depending upon that, I'm going to get thermal efficiency and the power efficiency or electrical efficiency, where Q dot is the useful thermal power output of the cogeneration system. Now, total energy, I told you, it is a sum of both electrical as well as it's a thermal energy, which is nothing but is the total efficiency of the cogeneration system. Now, I told you a few minutes back, now here in the numerator, I'm adding equivalent electrical energy and the heat energy, I think, which is actually not the proper way for comparing or deciding the energy equivalent, because both are not the same quality of the energy. Quality of the energy is different. And now total energy efficiency of the system, you can add up both its electrical efficiency and thermal efficiency. Then you will get the total efficiency of the overall cogeneration system. In the earlier, the very first or second slide, I told you the overall efficiency of the cogeneration system is, for example, thermal efficiency, I may be getting some electrical efficiency, maybe I'm getting some 40% and thermal efficiency maybe 50%. And then overall efficiency, it becomes 90% of the entire system. And 10% will be going as a waste if, I think if I'm right, what I covered in the second or third slide of this presentation. Like this, we'll get the overall efficiency of the entire cogeneration system. Now, what I just told you, it's the quality of heat is lower than the quality of the electricity, and it's decreasing because the heat potential, heat quality is decreases because it's a function of temperature. Higher the temperature, quality of the heat is good, and the thermal source will be good, and lower the temperature, it is lesser. Therefore, generally we are classifying the thermal systems into source and sink. Source is having high temperature, maybe quantum of the mass fluid will be the lesser, but sink is lower temperature, the quantity will be the higher. For example, if I take boiler or if I take a furnace, furnace is a source for a thermal power plant. And then the sink may be the flowing river water, flowing river on the downstream of the thermal power plant, because it's low temperature and maximum mass fluid system. But the quality of the energy is the very low. But in furnace or in combustion chamber, the quality of the energy is very high because the temperature is higher. Now, comparing, hence one may say that it is not very proper to add electricity and heat as it appears in above equation, as overall efficiency will be WE plus Q dot. If I'm taking W and Q dot, that means I'm putting electrical and what you call thermal energy together. But to get a 1 unit of electrical energy, we should know how many units of thermal energy we are spending. And now, therefore, it is not a proper way to add both the things. It's true that sometimes a comparison between systems based on energy efficiency may be misleading, and hence a thermodynamically more accurate evaluation and a more fair comparison between systems is we are going to use exergetic analysis of the systems. Exergy analysis of a thermal system is once again itself, it is a vast and broad area where we are going to approach or skip from second law of thermodynamics to go for what we call the exergy analysis for various thermal systems using energy third efficiency of the system, which is the actual correct way to exactly, we exactly knows how much amount of energy will be wasted without getting a work from that, and how much energy will be taken out to convert into any different works. and therefore the exergetic analysis or exergy analysis most required. Then exergetic thermal efficiency, now we can define it by a term called as exergetic efficiency, which is the ratio of E dot Q divided by EF, where E dot Q is the flux of exergy corresponding to the thermal potential of Q, and EF is the flux of fuel exergy corresponding to the mass of the fuel m dot F. And this E dot F, I have already explained, it is m dot F into D dot F, and specific exergy of a fuel, that is exergy per unit mass. Now, total exergetic efficiency, then you can add the thermal energy, that is the electrical energy, and the exergetic energy calculated from the thermal system. Because now what I did in exergetic analysis, I converted thermal or process heat energy, whatever I used, into an equivalent exact thermal energy, exact electrical energy, then equivalent to electrical energy, then I got the total exergetic efficiency of the system, which is nothing but the electrical efficiency plus the exergetic efficiency. Now, I told you a few minutes back, we are going to discuss there is a need of power to heat ratio in gas turbine combined thermal power systems. They got the power to heat ratio as 1.07. What it indicates, it is the ratio of the amount of electrical power produced from the system to the amount of thermal power from the system. That means this is called as power to heat ratio, or in some books or some literatures, they have given heat to power ratio. And generally in BEE manuals or Bureau of Energy Efficiency manuals for energy editing, they used everywhere heat to power ratio. But in research articles and in the textbooks or reference books, generally are in some standard data books, we are going to use a term called as power to heat ratio. Both are same, but one is reverse of the other. Then fuel energy savings ratio. Then we are going to discuss how much amount of fuel energy I am going to save by using a cogeneration system. For example, if I am going to extract energy, for example, I'll take an example of a thermal power plant, steam turbine power plant. So I am now, initially I have to heat a water of 1 kg, and to convert into the steam at 100 degrees centigrade, roughly I have to supply 2 to 56.7 of enthalpy of evaporation from and at 100 degrees centigrade. And once that steam do the work on the turbine and come back to the condenser, then it get condenses. And if I am not going to condense it, and if I'm not going to take that condensate back to the boiler, then every time I have to supply the total amount of enthalpy of formation plus the sensible heat of water, that is HF plus HFG, to the boiler. And if I'm going to take the condensate back and heat it that, or if I'm going to take that condensate back and heat the feed water or supplementary water required in the economizer, then the combined temperature of the water which is entering to the boiler will be increased. Instead of condensate temperature of some 50 or 60 degree at that saturation pressure of the condenser, it may goes to 70 or 80 degree if you use the economizer. To the economizer, I am getting the heat from the exhaust gas as a hot fluid, and then that heat I am transferring to the cold water, which is feed water to the boiler. Now the amount of heat I am extracting from the exhaust gas, otherwise it could have been wasted to the atmosphere, and that equivalent amount of fuel I am going to save in the furnace or in the boiler house, then that counts for me the fuel energy saving. And then that ratio, that means energy or the fuel supplied using an economizer and fuel supplied without using an economizer, will gives you the energy saving ratio. It gives you, that means how much amount of fuel energy you are going to save to bring the temperature of water from and at its 100 degrees centigrade to the saturation temperature. Similarly, the same concept we are going to use in all systems for calculating fuel energy saving ratio. FESR is nothing but the ratio of HFS minus HFG divided by HFS, where HFS is the fuel supplied to the system for separate production of WV and Q. That means if you want to separately produce the electrical energy, produce the thermal energy, whatever amount of fuel you are going to supply that, minus HFC stands for the fuel power for cogen system producing the same amount of W and Q. If you use exhaust gas from the chimney and reuse it in the economizer, then reuse it in the air preheater, then later on how much amount of fuel is required to be submitted in the combustion chamber, then if you consider that, or if you neglect the amount of heat, if you deduct the amount of heat recovered equivalent to its mass of the fuel from the total heat, then you will get a cogeneration amount of fuel consumed in the cogeneration system. Then always the amount of heat consumed in the cogen system for producing w.r.t and q.r.t, as that of you got it from non-cogen system, will be always lesser. Therefore, your fuel energy saving ratio is always less than unity. And 1 minus of that will give you how much percentage of fuel you are going to save in the system. In order for a cogeneration system to be a rational choice from the point of view of energy saving, it must be greater than 0. It must be greater than 0. We should not want HFC must be equal to HFS. Then there is no use of having the cogeneration system. Okay. Then other performance parameter. Prathamesh sir, how much time am I having?
Hello, sir. 10 to 15 minutes, sir.
Still I have 30 minutes?
Yeah, 15 minutes means after 15 minutes, 15 minutes for question answer.
Probably I am not getting time.
Up 12:30, sir. Up to 12:30.
Okay, thank you.
Yeah.
Then total energy efficiency of cogen system in terms of electrical efficiency and power to heat ratio can also be expressed by overall efficiency equal to neta E into 1 plus 1 by. In this case, the PHR can also be expressed in terms of electrical energy and the thermal energy. Then you can express the PHR in terms of overall efficiency of the system, the power to heat ratio. And significance of this PHR, it is acceptable values of power to heat ratio. It can be used when the electrical efficiency of a system is down at almost 90%. And power to heat ratio is one of the main characteristics of selecting cogen system for a particular application. Depending upon that, then how much, that means you will decide how much amount of power you want or how much amount of energy from the fuel you want in terms of electrical energy, and how much amount of energy from the fuel we want in terms of any thermal energy. Then accordingly, you can decide your applications, or depending upon application, you can decide your PHR or vice versa. And this is some of the summary. A few of the data I have collected from Bureau of Energy Efficiency, Government of India booklets. What is the heat to power ratio? They are using generally term called as heat to power ratio, HPR, instead of using a PHR. But heat to power ratio is not a common term. Actually, the PHR is a common term. That's why always we have to go for standard nomenclatures. The cogeneration system, here back pressure steam turbine, we discussed what. For it, the heat to power ratio is 4 to 14.3. And power output in terms of its percentage fuel input, it is 12 to 28%. And overall efficiency neta will going to get for 84 to 92. You see that whatever these power output values you are going to see, they are actually the individual efficiencies for which it is meant. And if you see the overall efficiency, they are efficiency after cogeneration. And then that's why you are having the cogen system is more efficient as compared to for what it is meant. Either it may be a bottom cycle or it may be in a topping cycle, but their overall efficiency will be the higher. Then this is some of the specific industries whose power to heat to power ratio will be. What is the range of that? In breweries, pharmaceuticals, fertilizers, and food paper industries. This is just for an information. We should know once we are going to audit or once we are going to calculate performance parameter of any system, we should know what is the approximate range or value it should get. we should get it. Whatever value we are getting, we should not closing our eyes. We can say that this is the value of your PHR or this is the value of your HPR. No, we have should know the range, and behind that, if it exceeds or it falls below that value, then there may be something problem either in the system or in the something problem whether in analysis or in calculation also. In a coil system, substitutes separate units of electricity and heat. Then we are going to use a term, what is the fuel energy saving ratio. Then if you substitute the PHR values in the earlier expressions, you can express the FESHR in terms of PHR 1 minus of PHR, some term in the denominator, which is again function of overall efficiency. And these are the formulas we are going to use separately for thermal system as well as separately for electrical system to calculating how much amount of heat I am supplying. And just to have a feel, then what did your FESR indicates? What your FESR indicates? Let us consider a coil system with a total efficiency neta is almost some 80%, and a power to heat ratio PHR is from 0.6. And substitute these values in a power plant, and you will get with a whose work efficiency and the work efficiency equivalent to electrical energy and efficiency equivalent to thermal energy is 35%. Then how much you will get a FESR? You see the FESR value you will get around 0.3 to 5. That means the coil system reduces the 35% of the fuel energy what you are supplying to the system. For example, if you are supplying some 100 kg of fuel, the almost 32.5% means 32.5 kg of fuel, we are going to reduce it by using cogeneration systems. Now, generally, these are all parameters what we have calculated. They are instantaneous values, or they are values which we are measured at some steady conditions, or the values which we are measured when the system is under normal condition or under steady state condition, but at particular time. But generally, the plant operating parameters will be checked for a duration of time. That means for first 3 months how it is working, for next 3 months how it is working, then next 6 months how it is working. We have to give the system performance on time range basis or on period basis. So generally when you purchase any cars or anything, they will say the first 3 years आपको maintenance बहुत कब आएगा, free आएगा. Then that means how first 3 years the system is working, what is its working performance parameter. Therefore, these are all instantaneous values what we are calculated. They are just meant for its instantaneous analysis at that point, how it is now acting. But how it is working in the entire span of its life, for that we should have an integral values. Generally, all these parameters we can convert into integral parameters, or the time specific zone parameters, the time period parameters. Either how my system is working in 1 hour, 1 year, next 1 year, next 1 year. Then those we can translate all these parameters into a time period parameters. That I mean to, sorry. In the previous equations, electrical, thermal, and fuel powers is used as per the for unit time, but it is necessary for us to go for on period basis, and they are called as an integral values indices. Then these integral values indices can be calculated by using same expression. We can use, instead of having a instantaneous time or instantaneous value, we can use the time period value, and you have to integrate, or you can take all the data and analyze it statistically and find its effective value for a duration of time. Then that is called as the what you call the period integrals. The advantage of this annual indices over an instantaneous or normal values what we are calculating will be these indices, or the annual values will give us how the system is performing, and this system performance depends upon load and environmental conditions. For example, if I say today's because of environmental too much cold conditions to generate a power output from a certain system, I may send the more fuel to the combustion chamber because the environmental condition is too lower, then the air is at a lower temperature to get the same required temperature of the air. When I'm going to burn in the combustion chamber, I have to send the more amount of fuel. Then automatically my BSFC or SFC of the plant will be suits up. But in the summer conditions, I have more atmospheric air temperature. Fine, I'm not going to spend the more temperature, more fuel. But the mass of the air entering to the system will be decreases because the specific volume of the air at higher temperature is the higher. Then the power to reduce power produced reduces. Then I have to pump secondary air at a high pressure. Then I have to optimize whether pumping secondary air at higher temperature will be more costlier or taking the cold air at a lower temperature such that the getting the more dense air is a more economical. That means I have to check the loading conditions, at what load the engine is or the system is giving more efficiency, and environmental conditions, how they plays the role. Everything will depends upon the values you are measuring. The degree of utilization of the energy forms, at what extent you are utilizing it. For example, if you are using any heat exchanger in the system, what is its effectiveness? Whether it is 20%, 30%, 40%, 60%. Then if you increase, for probably your heat exchanger is too old and it is not working, and then it is not working effectively. That time you take some readings and later on you replace it or you made the maintenance, taken the maintenance cares, and then the effectiveness of the heat exchanger will be increased. Then later on it's giving good results. In that case, you have to take the data of entire range of period. Then you have to take the average value of that. And therefore, it depends upon how effectively you are using the system. Initial selection or the design of a system, cogeneration strategy, what operational control, and the matching between the production and the utilization is also plays the role, or which will give the more advantages in the once you use the annual data. Annual indices are more revealing, or they give the more prediction of the actual performance of the system rather than what you call you are taking the instantaneous values. Typical cogeneration system performance parameters for different packages are given here for your reference. I'll share these slides with organizers. They can send it to you. And what are the instrumentation generally required for us for measurement of some test parameters or performance parameter? You can use the orifice flow meters for measurement of flow of steam, flow measurements like volumetric measurements or gravimetric generally we are using. And for airflow or flue gas measurements, we are using orifice meter or venturis or pitot tubes. Flue gas analysis can be done by different systems. We have nowadays gas analyzer, 5-gas analyzer, and handheld gas analysis also we are having. And unburned analysis, we can do it by gravimetric method. We can take the difference between the fuel admitted to the whatever the unburned hydrocarbons left after the combustion process. And then temperature can be measured by using thermocouples, or nowadays we are using a high temperature sensor, temperature guns. And cooling water flow can be measured by different flow meters. We have orifice, we can have wires, channel flows. And pressure, we are generally going to use button tube pressure gauge or any device where you can use the flow through different 2 points or single point pressures. The power can be used measured by energy meters, and the condensate can also be used by any flow measuring devices. And these are some of the observations you need to note down while you are testing. While you are testing going to record the performance parameters of the system. What parameters which includes thermal part and which includes the electrical part. Thermal part parameters maybe in terms of your steam inlet to the turbine. You may need to measure what is the steam flow rate, what is the pressure of the steam, what is the temperature, and then fuel input parameters to the boiler. You may measure what is the fuel flow rate. Generally, you can measure the combustion air flow rate, pressure, extraction of the steam at different points from the turbine, Brake pressure of the steam in the turbine you can measure. And condensing steam, condensate from the turbine, how much amount of flow is coming out, whether entire steam will be getting condensed or not. If not, then the steam will comes out along with the condensate, and if it is you are dumping it to the open uh, hot wells, then that steam will be wasted. Therefore, as much as possible, it's always better you should have the maximum amount of steam will get condensed. And the turbine bypass steams, sometimes we are generally using SRSG. You can going to measure what is the pressure of the gas and what is the temperature of the gas coming to that. Exit flue gas temperatures and other parameters you have to measure. Cooling medias you are using for cooling water and other things, for condenser and other accessories. That also you are need to measure it. And in electrical side, you are going to total power generation. What is electrical power? Hourly power generation system and quantity of power input from the utility grid. Sometimes you may need power to be taken from the grid for your some running some systems, and quantity of power generation from the DG sets, auxiliary power consumptions, and so many other parameters which are related to electrical systems also you are supposed to note down. And the test procedure for each cogeneration plant will be developed individually depending upon the type of the system, and it depends upon what are the types of instruments you are going to use. Generally, we are going to use 8 hours test data, and sometimes it may, if the system is very fluctuating or load and power consumptions will be varying continuously, then we may need to go for 24-hour data sampling collection. And here I have shown, going to share with you one or two case studies. One of the case study here I have taken, just I want to show you some brief numericals. A distillery plant having an average production of 40 kiloliters of ethanol is having a cogen system within a back pressure turbine. The plant steam and electrical demands are 5.1 tons per hour and 100 kilowatt. The process flow diagram as shown in the figure. Gross calorific value of the Indian coal is 4,000 kilocalorie per kg. Carry out that performs testing of the cogen plant considering efficiency of the turbo alternator 34% and efficiency of the alternator 92% and efficiency of the gear transmission system for power will be 98%. That means he's asking for you carry out the performance testing whether the system is using as a cogen system. Is it now we are going to use a boiler and then go for the turbine, and then if I use the cogen system whether it is useful to me or not. Just I'll show you. Initial calculations we need to find what is the total heat of a steam at turbine inlet at 15 kg per cm square 250 H1. You can go for steam table and calculate it. The total heat of a steam of a turbine outlet conditions he has given you. Outlet condition will be some at 2 kg per cm square 130 degree H2 is 648. The heat energy input to turbine per kg of inlet, then you get H1 minus H2. Then steam flow rate Q1 he has given rate flow 5100 kg per hour. Equivalent thermal energy you will get 86,000 kilocalorie per hour. Then energy input to the turbine, how much energy you are giving in terms of kilocalorie or kilowatts. You are going to calculate it by its mass and the flow rate. Then in 6 steps you are need to calculate the power generation efficiency of the aerator system. Then that is nothing but the output by input to that. You are getting the output is almost 86 and equivalent thermal energy what you are given as 86, and then input to that energy input to the system is you are giving 255 K times kilocalorie per hour. You get a 34% as a thermal efficiency. And efficiency of the turbine, that means the power generation efficiency of the turbo alternator he has given 34%, and other efficiency also he has given. Efficiency of gas gear transmission and efficiency of alternator will get 38%. Then quantity of steam bypassing to the turbine, then there is no steam is bypassed or tap from the turbine, therefore it is nil. The coal consumption of the boiler is 1550 kg per hour. Now in this case overall plant heat rate, though that means how much amount of what is the boiler system efficiency. we just discussed that what is the amount of total amount of fuel consumed, overall plant heat rate in terms of kilocalorie per kilowatt hour. That means total mass flow rate into change in enthalpy divided by power output of the system. You'll get 34068 kilocalorie per kilowatt hour. This always it is required for you wherever you are testing any thermal systems. You have to give the result and you have to give some remedies what to be done and what to be need to be improved. The plant heat rate is in the order of 34,000 kilocalorie per kilowatt hour because of the use of back pressure turbine. This value will be around 3,000 kilocalorie per kilowatt while operating on fully condensing mode. However, with a back pressure turbine, the energy in the steam is not wasted as it is utilized in the processes. The overall plant fuel rate, including boiler, is 15.5 kg per kilowatt. Then the remarks for this, the efficiency of the turbine generator set is as per the manufacturer specification. There is no steam bypass indicating that the power generation potential to steam is fully utilized. At present, the power generation from the process steam completely meets the process electrical requirements as per their power and capacity ratio. Therefore, the system is said to be balanced. Then this is the one of the little bit economic analysis problem for a thermal power plant. Just I'll rush through this one. Here the parameters given is for you for analysis, economic analysis of the cogeneration system, gas turbine operated and boiler installed plant with cogeneration system. He has given capacity of the gas turbine generator 4,000 kilowatt. Plant operating hours per annum will be 8,000 hours. Plant load factor 90%. Heat rate as per the standard given by the gas turbine supplier is 3049. Waste heat boiler parameters, unfired steam input 10 tons, 10 TPH. The steam temperature 200 degrees centigrade. Pressure will be 8.5 kg per cm square. Steam enthalpy 676. Fuel used is natural gas. Calorific value of the fuel he has given 9,500 kilocalorie. Price of the gas he has given 3,000 per 1,000 cubic meter. And capital investment for a total cogeneration plant he has given 1,300 lakhs. Now cost of capital and operation charges per annum will be roughly 298.63 lakhs. Then he has given the boiler data, cost of electrical power from state grid. Almost if you are not going to use the cogeneration plant, if you are going to buy the power, the grid is charging you 3 rupees per kilowatt hour with a capital investment of 10 rupees at 8.5 kg per cm square for boiler, it needs 80 lakhs. And if the boiler is fired by the natural gas. And for this, initial option 1 for me is gas turbine based cogeneration. To calculate what is the difference in cost for me with and without using the gas turbine based cogeneration system. Cost estimation, estimated power generation from the cogeneration system at 90% power factor will be plant capacity to number of hours the plant is operating will gives me some 288 10 to the power of 5 kilowatt hour per annum. Then to get this much amount of power, how much amount of heat input to the generator? I know that the heat rate is almost 288 and I know the units of that 3049 the data he has given. Then this is the total amount 878,333.76 I'll get. Then for this, how much amount of, to get this much amount of heat, how much amount of the natural gas to be required per annum? Then I know the calorific value. Then I know the total heat required. Then heat released equal to mass of the fuel into calorific value. I'll get the mass of the fuel. That 94.46 into the 5 cubic meter. The cost of fuel per annum, I know the cost, I think he has given 3,000 rupees per 1,000 cubic meter. They'll get 277.37. Then cost of capital, he has given 298. Then the overall cost This is the cost of capital plus the cost of the fuel. We'll get 576. The cost of power, I know the total power requirement is 4,000 for 8,000 hours. Then divide by 576 will gives me roughly 1.83 something, and he has rounded up to 2 rupees per kilowatt hour. Now, if I go to the second option, electrical power, if I don't use the cogeneration system, then cost for getting the power from the grid is 864, because 288 into 3 if you do. Then the fuel cost of steam by separate boiler, steam quantity, how much I'm going to farm, 10 TPH he has given, then 8,000. So much amount of heat input for 541152. Heat input required to generate 10 TPH steam will be 601280. The natural gas quantity required for that will be 63.29. Then the cost of the fuel will be 189. Then if I sum up this total cost, I'll get some almost the 1053 lakhs per annum. The total cost for section for alternative system. So this results gives me the total cost for option 1 is 576, and that for option 2 will be 1053, and then the difference will be almost 477.8 lakhs. And I can conclude with this, in case of option 2, there will be some additional impact on the cost of steam due to capital cost for a separate boiler. And option 1 is the economical compared to option 2, because the electricity from state grid and the steam from natural gas fired boilers are not what you call feasible. With this, these are some references I have been used for this work. And thank you very much. I hope I took 2-3 minutes more than time given to me. Thank you once again for RJT management, Principal Professor Bokade, and Head of the Department Professor Kale, and Prathamesh, Amol, Sambhaji, and Ashwini Madam, Atul Sir, and others. Thank you very much.
Yes, thank you, sir, for your excellent insights on this performance analysis of the cogeneration systems. Now, with your permission, sir, I would like to take a few questions from the participants. Yes, sir. So the first question is from Mr. Satyamurthy GL. He's asking, can you suggest the cogeneration plant for treating municipal solid waste?
Cogeneration plant for utilizing the municipal solid waste. Again, it depends upon whether it is the solid waste will be separated in different way. It may be, then for that you can go for a waste heat recovery open boilers. Generally, the people are using the water tube boilers for wastewater heating and other things. Sorry, so for water heating. Or you can use, hello?
Yes, sir, we are listening, sir.
SRSG system. But for municipal waste, the one thing you can keep it in your mind, the separation of the waste is most important for you, and drying it and pelleting it. Then you can, that calorific value of that is very less, then better. We are not going to use for a what you call the power generation system. You can use for the process heating and other things. Generally for water heating and other, it's a good option.
Yes, sir. Sir, there is one more question from Mr. Satyamurthy GL himself. The question is, what is the minimum and maximum capacity of the cogeneration plant?
Minimum and maximum capacity of the cogeneration plant, we can access its power to heat ratio. That it may goes to up to 1.7 or 1.8. Like that, there is no capacity of the cogeneration plant. The cogeneration plant is meant to how much amount of energy you are recovering from the waste from the basic source. And therefore, we discussed that there are top up and bottom type of systems. And generally in bottoming type, 15% loss will be unavoidable, 15 to 20%. But in top of systems, you can extract 100% heat from the waste systems. And again, its capacity depends upon your source heat. You can go to as low as possible. But what is the source for you? What is the source exit temperature? For example, I told you bottoming from 1200 to 600, then you will go to up to even 150 temperature is also available to you. The capacities, we are not going to say the capacity, we are going to say the percentage of that. How much percentage of the energy available we can recover it in the cogeneration system.
Yes, sir. Thank you for your answer, sir. Now I would like to hand over to Professor S.D. Gaikwad.
Thank you, Padma sir. It is my privilege to propose vote of thanks. On this occasion, I, Sambhaji Gaikwad, on behalf of MCT's Rajiv Gandhi Institute of Technology, Department of Mechanical Engineering, and on behalf of Organizing Committee of AICTE AQIS, sponsored online 1-week short-term training program on recent trends in energy management and audit. And my own behalf extended a very hearty vote of thanks to Dr. Siddappa Bhusnoor for accepting our invitations as a resource person and sparing his valuable time with us. Sir has given good insight on the topic of performance analysis of a cogeneration system. Thank you so much, sir.
Thank you very much.
Thank you, sir. Thank you, sir.
For giving us an opportunity.
Yes, thank you, sir. Next session start at 2:30 p.m. Please join all participants. Technical team to end the session.
Thank you, Bhusnoor sir.
Thank you, sir. Thanks a lot.
Thank you, sir.
Thank you, sir.
Thank you, Amal. Thank you, Prathamesh. Rajesh, sir, thanks.
Yes, sir. Yes, sir. Thank you.
Bye. Can I leave?
Yes, sir.
Yes, sir. Yes.